You've probably heard someone call a computer's processor, the CPU, its brain. Then, it's a great shortcut. But what does that really mean? How does a little chip of silicon actually think? Well, today we're going to pop the hood and see what's really going on inside. So let's just start right there. When you're clicking around, playing a game, whatever it is you're doing, what is that CPU actually up to? It's not just one big thought. It's this non-stop, unbelievably fast process happening every single second. To really get it, you've got to look inside. And honestly, the best way to picture a CPU is to think of it like a tiny, super efficient workshop. And just like any workshop, it's got a few key players, and each one has a very, very specific job to do. So it all boils down to these three main parts that make all the magic happen. You've got the control unit, the arithmetic/logic unit, which everyone just calls the ALU, and something called the registers. Each one is absolutely critical, and they all work together in this perfectly timed dance. Okay, first up, the control unit. Think of this as the project foreman of our little workshop. It doesn't do the math or lift the heavy data itself. Nope. Its job is to read the instructions, from a program or your mouse click, and then tell everyone else what to do. It's the traffic cop, directing the flow of everything. Next, we've got the ALU, the arithmetic/logic unit. Now, this is the powerhouse. This is the workshop's ridiculously powerful calculator. Anytime your computer needs to add two numbers or check if one thing is bigger than another, any kind of math or logic, it happens right here. This is where the actual thinking gets done. And finally, we have the registers. If the ALU is the calculator, the registers are its super high-speed workbench. They're these tiny little storage spots that hold the exact piece of data the LU needs, right at that very second. Their incredible speed is what allows the whole operation to run smoothly, without any delays. Okay, so we've met the team, the foreman, the calculator, and the workbench. But how do they all work together? Well, they follow this constant, repetitive four-step process for every single tiny thing your computer does. And that process has a name. It's called the machine cycle. It's this simple, elegant loop: fetch, decode, execute, and store. That's it. Every single action, from the most complex video game graphic to moving your cursor one pixel, is broken down into these four steps, repeated billions of times a second. Now, check this out. That four-step cycle is really split into two phases. The first two steps, fetch and decode, that's called instruction time, or I time. This is all about getting ready, figuring out what to do. The next two steps, execute and store, that's execution time, or E time, and that's about actually doing the work. This split is actually a huge deal for making computers faster, and we'll see why in a second. So in that first half, the I time, our foreman, the control unit, takes charge. It reaches out to your computer's memory, fetches the very next command it's supposed to handle, and then decodes it, basically translating it into a language of simple on-off signals that the processor can actually work with. Then boom, we're in E time. The now decoded command is passed over to the ALU, our calculator, which performs the operation. It does the math, makes the comparison, whatever the job is. And as soon as it's done, the result is immediately placed in one of those super fast registers, that workbench, all ready for the next instruction. All right, so that's the process: fetch, decode, execute, store. But what really makes one computer's brain faster than another's? It's not just about having a process, it's about how insanely fast and efficiently that process can run. So let's talk about what puts the speed in processing speed. The number you always hear about is clock speed, right? You see it measured in gigahertz or GHz. Well, all that is the rhythm, the heartbeat of the processor. It's literally just a measure of how many of those complete four-step machine cycles the CPU can pull off in one single second. So what is 1 gigahertz? It's 1 billion. 1 billion complete cycles every single second. So when you see a processor that's, say, 3 gigahertz, it's doing that fetch, decode, execute, store dance 3 billion times a second. The scale of it is it's almost impossible to wrap your head around. But here's the thing. Just cranking up the speed can only get you so far before you run into some serious physical problems. So engineers had to get clever. They had to figure out how to make a processor work smarter, not just harder. And one of their best tricks is something called pipelining. It's a fantastic idea. Instead of waiting for one instruction to go through all 4 steps before starting the next one, the CPU sets up a kind of assembly line
where different instructions are all in different stages of the process at the exact same time.
This chart shows it perfectly. Just look at what's happening in cycle 3. In that one moment, instruction A is being executed by the ALU. At the same time, instruction B is being decoded by the control unit. And at the same time, instruction C is just being fetched from memory. 3 jobs are getting done at once. It's a massive efficiency boost without even touching the clock speed.
Of course, the other giant leap forward was multi-core processors. The thinking was pretty simple. If one of these workshop assembly lines is good, why not just build 2 of them, or 4, or 8, or 16, all on the same chip? Each one of these cores is basically its own little processor, ready to share the total workload.
So if we go back to our analogy, it's literally like having multiple workshops running side by side. This is exactly how your computer can be streaming a 4K movie, running a virus scan in the background, and keeping 20 browser tabs open all at the same time without breaking a sweat. Different cores can tackle different big jobs. But there's a catch. All this incredible speed, these billions of calculations every second, these clever tricks like pipelining and multiple cores, it all comes at a price. A very real, physical price that every computer designer has to fight against. And that price is heat. Think about it. All of those electrons zipping around, flipping switches billions of times a second, that generates a massive amount of waste heat. And heat, as you probably know, is the absolute mortal enemy of electronics. So how do we fix this high-tech problem? Well, the solution is surprisingly basic, a heat sink. It's really just a chunk of metal, usually aluminum or copper, with a bunch of fins. You stick it right on top of the CPU, and it literally just pulls the heat away from the chip so it can drift off safely into the air. And that really brings us to the big takeaway here. A CPU is an absolute marvel of engineering. It's a tiny universe of logic that operates at speeds we can barely comprehend. But all of that incredible power is constantly in a delicate balance between its own complex operations and the very simple, very real need to just stay cool. So I'll just leave you with this final thought. A modern processor can simulate the birth of a star or design life-saving drugs. It can create entire worlds out of pure logic. But for all of that godlike power, what's the one thing it absolutely cannot do without that simple piece of metal on top? It can't escape the heat.